What do you think? Which band contributes to the conductivity? An empty one, filled with electrons, partially filled, or there is some other option? In this lecture, we're going to learn about semiconductor conductivity. And the topics that I would like to discuss today are the energy band model, where it comes from, since we're going to talk about it at several occasions again. Then the conductivity in semiconductors, how do we define it and what does it depend on? Especially for devices, it's important also to have a good understanding, because actually the operation of the devices, of semiconductor devices, is all about controlling the conductivity, whether we want the switch to be on or off. Then concentration of charge carriers and with generation and recombination, that's two of the topics that influence the conductivity. This is combined in the continuity equation that describes the concentration of charge carriers. Then there is also the second part to the conductivity is the mobility. So charge carrier mobility and the charge transport that can be through diffusion or drift. You can see here is the different types of conductors for different materials. We have in the third column resistivity in units of ohms times millimeter square per meter, and then temperature coefficient. What do you see here? What are the features that you see from this table? So for example, you can see the difference between conductor and insulator, the resistivity, right? So that's quite obvious. Now, in the last column, what can you see there? Is there anything worth noticing? For sure, we don't speak about the exact numbers of this temperature coefficient, but we can see that for conductor, the temperature coefficient is positive, whereas for the semiconductor, it's negative. So that means when the temperature increases, the resistivity is reducing. Sounds pretty well and interesting. For resistivity, if you have these numbers and you would like to really calculate the resistance of a material, then you take the resistivity, multiply it by length, and divide by cross-section area. So that's simply how we use it. So the story about this different temperature coefficient sign in front of the semiconductor starts at the atomic level, where we have to understand the energy bands. So this is a simple model of a silicon atom. We have the nucleus and 14 electrons around it. For each electron, there will be a defined quantum state. It's defined by the 4 quantum numbers, and no 2 electrons in the system can have the same set of quantum numbers. So starting from the single atom, that's valid, but also for a system of atoms, it will be the same. Here we can see from the bottom the nucleus, which is the lowest energy levels defined for the electron. And then as the electron can move further away from the nucleus, that means it has higher energy. For 1 line, then 2 lines, then 3 lines above. These are the shells related to the principal quantum number. Then in each shell, we have several orbitals. From 1 up to the highest level I have drawn, it's 4. Actually, for the silicon atom, typically we will have the first 3 occupied. So the number is shown in the table. And then this angular momentum, the orbital, every orbital will have a different shape. And these shapes also define magnetic quantum number. So what I'm drawing here is for the first orbital, we can have 2 electrons on each orbital, one with the positive spin and one with the negative spin. So this is the first number, the spin. Then if we add the considerations of the second quantum number, which is the angular momentum, we can place there 3 pairs of electrons with spin up and spin down, because that's what the magnetic quantum number tells us, how many pairs we can place there. Then if we go to one higher orbital, we can add 2 more pairs, because again, it's defined by the magnetic quantum number, and so on. But the number of filled electrons is also depending on which atom, which atomic numbers we are talking about. Now, if we take 2 atoms, each of them is defined with certain potential fields. It's defined by the wave function. And if we take a separate atom, like isolated from the system, it has certain wave function, and another atom would have it described exactly the same. But when we put them close together, then those wave functions overlap, and then there is an interaction between them. And because of when we remember that there is this Pauli exclusion principle, but that not 2 electrons can contain exactly the same set of quantum numbers, something has to happen so that we can accommodate in the system all those electrons. So effectively what happens is the energy levels split, and we have additional energy levels. Why I put the cyclist there is to show analogy. You can imagine a single cyclist going around the track, and to have certain speed, then the cyclist has to put the energy. And another cyclist will have to put exactly the same energy, assuming that they have exactly the same weight and bike and friction and so on. But if we have now 2 of them on the same track, one running, so cycling after the other, then we have this draft effect, that the first one has to put a bit more energy, and the other one can have a bit less energy, and they still together, they go at the same speed. So this will not work, this analogy will not work when we talk about 10 cyclists. Then we have to forget about this simplification, but with the atoms it still does work. So if we have a system with multiple atoms, and that's what we have in crystals, that is what we have in the semiconductor, then each of the atom alone has the same set of energy levels, but then when we consider them all together, then we have to have the shift, the split in the energy levels so that we can accommodate all of the electrons in the system. So this creates these energy bands. And especially strong shifts we will see further away from the core of the atom, where the influence of on the wave function due to nucleus, close to nucleus, this influence is very strong. Especially at the furthest orbital, it's more, on the further shell, it's more significant because there the electric field and the interactions with the nucleus, it's not so strong. So if we consider a crystal, we have to also, so this is all very simplified because crystal is a certain periodic structure, but it will not look exactly the same in all the directions. So we have all possible angles of directions. And so this can be simple. What I would like to do is to simplify it a little bit. So we look in just 1D direction, position, and energy as a function of the position. And every time we have a nucleus, there will be the quantum well, and then we have what you can see in the brown lines here. But what's the most important for us is the valence band, which is the last band that is occupied in the atom. And then we still have other energy levels, but typically they are not occupied, and this will be our conduction band. So in the valence band, we will have electrons, normally in the conduction band not, as long as we consider the 0 Kelvin. The unit of the energy here that we use is electron volt. And what happens is if electron gets enough energy, it can get promoted to the higher energy level. Again, looking at these energy levels, these energy bands, we have the lower bands, valence band, and conduction band. We can even tell what is the number of states in the band. It's the minimum number of states will be twice the number of atoms in the material. But what's interesting for us is how the occupation of the bands contributes to the conductivity. So what do you think? Which band contributes to the conductivity? An empty one, filled with electrons, partially filled, or there is some other option? Who votes for partially filled? I will show you a nice analogy about that. So yes, the partially filled are the ones that are good for conductivity. So imagine a jar. If it's, we have some jelly babies inside, and we can shake it. If it's completely empty, we can shake it and there will be nothing. There is no motion. So obviously, an empty one, the A, was not at all correct. What if it's completely filled? Like we want to get as many as we want in the jar, as we can in the jar. We fill it completely and we shake, and nothing. There is no motion. So a completely filled band won't be good for conductivity either. So that's what we have in the insulator. We will have either completely empty or completely filled, and there is no conductivity. A good metal will be such that it has partially filled valence band. Those are metals like gold, for example, or copper. And we have also some metals belonging to category of semi-metals. So here the energy bands are overlapping the valence and the conduction band. But when we look in detail what happens there, we will see that these are not as good conductors. So also when we look at the resistivity is much higher than in these good metals where the valence band is partially filled. We talk about semiconductor, but in the end, is it conducting or not? And that very much depends on the operating environment. So that means the temperature, the applied electric field, but also other things like the external energy that we can also deliver through light. So if we want to learn about the conductivity of material, and specifically here for semiconductor, because lots of things can happen, we have to look at the bands and how they are filled, the energy bands. So first thing is, how many electrons can be placed all together in each band? So that is the density of state that is available in the system. And second, how many places are actually populated? So that's the probability that the state is occupied, because with electrons we can just talk about probability. We don't know for sure. If we look at different materials, then the energy gap between the top of the valence band and the bottom of the conduction band will be changing. And because of that, also we see the different properties, different conductivity of the material. For example, when we say we look at the same temperature. For silicon, it's 1.12 electron volts, whereas germanium is much lower. So detectors that are used for germanium, they are cooled to low temperature so that we don't have charge carrier generation due to thermal effects. Whereas gallium arsenide, they are typical high temperature semiconductors in the environments where, like industrial or automotive, in some places there is no other choice than using this type of semiconductor. That's because it has high energy band. And for all of those materials, near 0 Kelvin, well, except maybe from silicon dioxide, it's not even a crystal, so we still have some thermal generation, but it will be much more complicated. So near 0 Kelvin, we have the valence band completely filled and the conduction band empty. As we increase the temperature, we have this thermal generation. And you can say, but I know that at room temperature, at 300 Kelvin, the thermal energy is 26 millielectron volt. So what is it? How is it that we have this energy gap of 1 electron volt in silicon, and if at room temperature already we have charge carrier generation? Anybody can explain? or it's already the gut feeling that tells you. The thermal energy is the mean energy of charge carriers. But always we will have some that have this, then they can reach higher energy, and those can be promoted to higher energy levels. So luckily, not all of them, because we couldn't make any use of the semiconductor at room temperature. So what happens is, for example, for silicon, but also any other material, in fact, at 0 Kelvin, is for any semiconductor, there will be no charge carriers at 0 Kelvin, but as the temperature increases, and you can see there is this vibration of the lattice, then because of that, there will be energy passed from phonons, and the electrons, they can get the energy, the thermal energy, and get promoted to the conduction band. So that's one way how it can happen. The thermal vibration breaks bonds between the atoms. Then we have the liberation of electron, which is equivalent to generation of 2 charge carriers. So one is the electron that can move in the conduction band from one atom to another. And there is also a hole, which is the lack of the electron in the valence band. And at the place of the hole, another electron from neighboring atom can jump in that place. So we have effectively 2 charge carriers. And if we look at the distribution over the energy, so that we get to the topic of the probability, then in the near 0 Kelvin, we are sure that all the atoms are in the valence band, and none of them are in the conduction band. Whereas, as we increase the temperature, then some electrons will be moving to the conduction band, and then this distribution, called Fermi-Dirac probability, it will get smoothed out. So that's how we can symbolically show the occupation, the probability of occupation of electrons in the valence band or in the conduction band. Now, if we flip it, then we can have a more usual version of showing the probability. So probability minimum is 0, maximum is 1. And then in the x-axis, just like in the corner picture where we have the valence band, is the energy. And here we have normalized by the Fermi level, the Fermi energy. So Fermi energy is the one that is exactly it's almost exactly in the middle. We can assume it's in the middle, and it's where this crossover of all the curves happens. And then as we increase the temperature, we have more and more uniform, maybe not uniform, but we can see the tendency in the distribution of the charge carriers. What I always like is the simplifications, and I think everybody appreciates that. Usually when you read about semiconductor devices, where we will be talking about the Fermi energy, it's still important, but we don't operate with this probability model, which is the Fermi-Dirac distribution, because it describes quite precisely what happens in the middle of the energy gap, but we really care about what's below the top of the valence band and what's above the bottom of the conduction band. So we can make some simplification, and we will say we only discuss the energies that are so far away from the Fermi energy that it's much greater than k times t. So Boltzmann constant times temperature. And if we do that, then you easily see that this function simplifies to the form of exponent of EF minus E divided by KT. And what it gives us on the plot, you can see the dotted line. They are not connected. So the part that it's not well defined in this approximation is here in the middle. But further away, as we move away from EF, you can see that the dotted line and the continuous line, they merge together. And this is the region where this approximation is valid and where we can use it. So this is so-called Boltzmann distribution. So what we have to consider now, speaking about the conduction of material, is what is the charge carrier concentration. And again, we already have seen that for different materials, the energy gap is a little bit different. And we can see the effect of that when we plot the charge carrier concentration as a function of temperature. At the moment, still simple, so it's somehow we can conceptually see that it's much faster increasing concentration in germanium than in silicon, and in gallium arsenide, even at high temperatures, we can see that the charge carrier concentration will be always the lowest. And that's because of the difference in the energy band gap. So for the conductivity, one thing is the density, and the other the probability. So the density of available state, and the other is the probability. That's what we have already seen in the previous slides. So for the charge carrier concentration, we multiply the density of states and the probability. So density of states comes with the material, the crystal structure, but also there is temperature dependence. And probability is mainly temperature dependence, but we will see the expressions. So effective density of states in the conduction or in the valence band. So for each band we can describe it separately. It depends on the temperature and the effective mass of the charge carrier. So for holes and for the electrons it's slightly different. And then the number of charge carriers, we have the number of states times the probability, which is from our Boltzmann distribution, because we look deep into the valence or into the conduction bands. For an intrinsic semiconductor, so one that is just pure germanium, pure silicon, pure gallium arsenide, so we don't add any other atoms that really change quite a lot the behavior, and they can control the conductivity. If we still consider just the intrinsic, then the charge carrier concentration for electrons and holes, it's the same. It's simple, right? We emit electron to the conduction band, we have hole in the valence band, and it always has to be the same. We can also look at this charge carrier concentration as a function of temperature in the so-called Arrhenius distribution, where it's not actually the function of linear temperature, but 1 over temperature. And then we can see that actually it's a nice format to display it because it's linear. So from linear plots we can get much easier parameter extraction to get their characteristics. So that's basically the same. What I would like to point out here, because it's logarithmic, so we can see a bit more clearly the difference that it reaches orders of magnitude. For silicon at 300 Kelvin, we have 1.45 times 10 to the power of 10 per cubic centimeters, numbers of holes and number of electrons. In germanium, it's 3 times higher. And keeping in mind these numbers, when already I mentioned doping of semiconductor, where we can add atoms of different materials, that gives you already the idea how many atoms per cubic centimeters we have to add in addition, so that we add additional holes or just additional electrons, so that we can control the conductivity. It has to be above the intrinsic charge carrier concentration at the temperature where we use it, because of course we can see that it's strongly temperature dependent. If we want to calculate the resistivity, this is still not enough, because the resistivity, it's not only the number of charge carriers, but also the mobility. We can compare it to a vehicle. A vehicle will not go faster when it has more wheels. We also have to do something with its mobility to make it go faster. For the thermal generation, I think that it's good here to add. I think I wanted to show the fact that the electron can be moving from valence to conduction band not only by thermal emission, but also if we emit photons. So if we illuminate the semiconductor with photons, we can observe the change in the conductivity. So what we sometimes have as a tricky problem in the lab, if we work with integrated circuits, in a ceramic package we can open the cover of the package to see what is on the chip. We can also place probe in order to contact specific pads in the chip. But if it's illuminated, it will not behave exactly the same as in the dark condition, because we have extra generation of charge carriers. So we have to put it in a dark place. The picture reminds me of something else. So we're talking all the time about the charge carrier generation, but I mustn't talk about the recombination. So if we had always generation of charge carriers because of the thermal effects, the thermal energy, then in the end we would have all the electrons ending up in the conduction band. But it's not like that. We will have certain lifetime of charge carrier, and recombination also happens. Also when we cool down the semiconductor, because the recombination and generation, they are both temperature dependent, we will have a stronger recombination in the lower room temperature. Now we can come to the continuity equation. Yeah, that was what we needed, generation and recombination. So charge carriers, they have to have certain continuity. They don't suddenly appear or disappear. And the charge carrier concentration over time is described by the generation rate, recombination rate, that would be in the simple condition when we have no current flow, but in addition we will have currents, and the currents will they contribute to additional charge carrier concentrations that come from different locations.
You're the signal in my static hum, a perfect match we've overcome. Wires cross, but we still